применением фотоника интегральных схем по устройствам, которые на основе их созданы и работают, принципах работы, применению и в том числе преимуществам. Сегодня мы продолжим рассказ про микроволновую фотонику, про различную фотонику, потом про биофотонику, одна глава, и третья лекция уже по общим применениям. Отдельно всем возможно, если останется время. Okay, Паскаль, we can start right now. Just let me announce them and ask questions about translation if they need.
Okay.
Сейчас лекция будет преимущественно на английском языке. Это только что-то непонятно становится, поднимайте руку, останавливайте, начинать переводить или пояснять. Хорошо?
Okay, thank you, Juliana. Good afternoon, everybody. Welcome back again to this series of lectures on applications of photonic integrated circuits. Yesterday we covered an introduction to the ecosystem and as well an introduction to microwave photonics, but we also saw not only microwave photonics with discrete components, we also saw some application-specific chips. We ended with this slide showing that this is a generic system of microwave photonics on a chip. All functions can be done with this system. And the demonstrations so far which require these components in this system have been only done in integrated circuits partially, with a degree of integration around 14–20%. Okay? So today I'm going to talk about multifunctional integrated microwave photonic chips. And the contents of this part are central role of photonic filters and then three photonic IC application examples. So let's go to the filters. This is the generic scheme that represents a microwave photonic system and that can be put on a chip. We saw this yesterday, but just to review and for those that were not present yesterday, optical source, that can be a laser, broadband source, etc., source shaper, modulator, coupler to have optical control of what's going inside your system, a reconfigurable filter, optical out of your system maybe, detector, and then all the electronics associated, plus control electronics. Okay? So one of the key elements in these systems, besides of course all the actives, laser, modulator, detector, etc., are the filters. This filter, but mainly this filter position here. These filters provide the key functionality of your microwave photonic systems. The other elements are just to put your systems, your signals, in the photonics domain, from the electronics to the photonics domain. So yesterday we also saw that different types of filters can be done in photonic chips. These are pictures of actual photonic chips, like a couple resonator optical waveguides, cascade Mach-Zehnder interferometers, and ring-assisted Mach-Zehnder interferometers, where you have different photonic building blocks, couplers, custom couplers, 3dB couplers, and phase shifters. This we saw yesterday. So today I wanted just to give a little bit more of insight on this type of filter, which is very versatile. As I said yesterday, you can synthesize nearly every filter response with this filter architecture. Okay? This filter architecture is composed, as I said, of two 3dB couplers in a Mach-Zehnder configuration, but the arms of the Mach-Zehners are loaded with ring resonators. These are ring resonators. And the degrees of freedom for design in this architecture, in this filter architecture, are the phase of each ring resonator relative to each other. Basically, that can be done either changing the length or tuning the phase with an active tuning element. The coupling constant between the Mach-Zehnder arm and the ring resonator, that again can be set with a fixed coupler, or you can put a little Mach-Zehnder there to tune the coupling constant. And then as well, the phase imbalance between the upper arm and the lower arm. In any case, this filter is totally equivalent to a digital filter. Yesterday I mentioned digital filters. If you are not familiar with, never mind, because there is a very good thesis from our group and a very good book where you can learn all this. But just imagine that you can use digital filter design techniques, the ones that you use in digital signal processors and that are very well known, to synthesize your response. Okay? So basically, you can go, for instance, if you are familiar with MATLAB. If you are familiar with MATLAB, MATLAB has a digital filter synthesis tool. you can use that synthesis tool, and that will give you the filter coefficients. Okay? And then you can resort to the book I have mentioned or to the thesis I have mentioned, and there is a synthesis algorithm that will translate these digital filter coefficients into the physical representation of the photonic filter. Okay? It will translate the coefficients into the coupling constant, the phases, and the imbalance between the MZI. Okay? So basically, using digital filter techniques and a synthesis algorithm, you can make a photonic integrated circuit filter. That's the message. Okay? Of course, the process is a little bit, let's say, elaborated, but as I said, it is pretty detailed elsewhere. And there are things that, of course, you need to consider. First of all, this is an ideal design, and then the ideal design assumes that everything is perfect. The phase is exactly what I said. The coupling constant is exactly what I said. What happens if there are errors in the phase, or errors in the value of this K, this phase, etc.? Well, basically, this is the ideal filter, and this is what you would get, more noisy filter. Okay? When you have deviations, basically think that this requires interference of light inside the device. For those precise values, the interference is perfect. If you change slightly those values, then there appears some, let's call it noise. It's not exactly noise, right? It's imperfections in the filter. Okay? That is one source of imperfections. That, of course, when you fabricate it, it is not exactly what you design. Even when you tune it, you cannot get it to the ideal point. So ideally, you would get the black trace, but in practice, it's likely that you get the gray trace, even worse. And there's also something that this design procedure does not take into account, which is propagation loss. Ideally, in digital, you can pass one coefficient to the other without any loss. I mean, if it is one in the next block. Okay. But in physics, that is not true. I mean, if you have light here and it goes one round trip, it has loss. Okay, so when it has loss, what happens to your filter? Basically, it gets rounded. Okay, of course it loses, but it gets rounded. Something that you don't want. You want your filter as perfect as possible, as square as possible. So it gets rounded. The more loss it gets more rounded. At some points, even you can lose the filter at all if the loss is too high and your filter is too selective. Okay. Now a little bit of recall on the building blocks that are used for this filter. I said couplers and ring resonators. So basically the couplers, custom couplers, we discussed them when I was here in October. They are MMI couplers, but with a fancy shape in the middle. They are not rectangles, okay? But they have this widening in the middle, or even this, stretching, widening, stretching, okay? And then those can provide any coupling constant as you wish. For instance, here there is one which is 5248 or 5149. Here 8515, 9505, and 8515 again with other architecture. So those things can be easily done, easily designed with software that some of you have available, like the Phoenix software. We have designed them, we have fabricated them, and these are actual measurements, so they work very well. Okay. So the design techniques are summarized in this paper, and they can be done easily. Other thing that you have are the ring resonators. These are these small rings here. So you can see them here. Okay, these rings here. And you can see the metal pads going on top of the rings. These metal pads are for tuning the ring. You put current on one pad and it flows to the other pad. So actually it hits the circuit underneath. And that causes, this is the response of the ring resonator, and that causes the response to shift. Okay, these were measurements that we did last couple of weeks ago with some indium phosphide chips, and basically with 9 ppi, it's equivalent, not equal, that is wrong, equivalent to a current injected of 9 milliamp. Okay. Then that was for the regular ring-assisted machine filters. And as I mentioned yesterday, those filters are reconfigurable. You can make nearly every transfer function that you wish, but they are Ramsey filters. They are not couple ring resonator filters. They are not Mach-Zehnders. So actually, once you set to this architecture, once you draw your circuit, it is always this architecture. Once you draw your Mach-Zehnders, they are always Mach-Zehnders. Once you draw your rings, they are always rings. is there an architecture that can change, that can be reconfigured to be this, or this? And the answer is yes. Okay? And this is something that we are doing currently at research level, not yet very mature, but actually is this sort of mesh.
Let's try to ask them.
Okay. Okay.
Вопрос есть, все понятно, непонятно. Тем, кого вчера не было, мы начали рассматривать тему о том, что для передачи приема сигнала нам нужен лазер, модулятор какой-нибудь СВЧ, фильтр, набор фильтров, или для перестройки сигнала, для модуляции сигнала по фазе какого-то, например. И дальше уже приемник. И мы начали рассматривать отдельные части одну за одной. В качестве фильтров могут быть использованы кольцевые резонаторы. Но кольцевые резонаторы, как было показано в предыдущем слайде, они заданной топологии, не могут изменяться, не могут выполнять другие функции. Если мы хотим, чтобы устройство одновременно выполняло несколько функций, в отличие от текущих интегральных схем, когда одна схема разрабатывается для какого-то конкретного применения, если мы хотим расширить применение одной конкретной схемы, то вот группа разрабатывает устройство, которое может быть одновременно и фильтром на основе кольцевых резонаторов и одновременно набором из интерферометров Баха-Зандра, которые могут выполнять дополнительные функции. Это лучше чуть-чуть. Okay.
What?
Could you pronounce slowly?
Slowly? Okay, I'll try. Okay. So, I was saying these are fixed architectures. Basically, when you draw them physically, they are not going to be, cannot be this one, okay? And we are researching on a new architecture, which is this hexagonal mesh. This hexagonal mesh, actually, each of these lines is a Mach-Zehnder interferometer, a 2x2 Mach-Zehnder. So you can set it in bar state, in cross state, or you can even set it in, I don't know, 10%, 90%. So it's a tunable Mach-Zehnder, since it has some heaters on top of the arms. Okay, so this is the basic unit, the basic tunable unit, and then you draw it or you combine it in a hexagonal mesh. And with this mesh that you can see here, this is the layout. This is the actual circuit with the wire bonds for all the Mach-Zehners, the wire bonds, and this is a close lookup of this mesh here. You can see the Mach-Zehners there, and hexagonal mesh, and this is the actual circuit with the PCB. With this mesh, you can make, for instance, a Mach-Zehnder, because you set this Mach-Zehnder and this Mach-Zehnder are in tunable mode, as a tunable coupler. Okay, these are as a tunable coupler. These are in cross states, and these are in bar states. So actually, you have this path in, and then short arm, long arm, and then out. One and out two. Okay, that's a Mach-Zehnder. And then it is not easy to see, but you can also make a scissor filter which consists of two rings coupled to one and two waveguides. They are not coupled in between them, they are apart. Okay, and this can be done with this configuration: in and then this way out. This is one ring, and this is the other ring. Okay, and this is the second one. Okay, so it's a totally reconfigurable architecture. It's a generic architecture, and that is what we are researching in having as much as possible degree of freedom in our microwave photonic system. Please recall, this is going to be this part. Okay, so this part, if it is totally reconfigurable, that means that you have a generic processor. Okay, so you can have a tunable filter, you can have an intermediate frequency measurement system, a transceiver, whatever. Wherever there are a function that you are looking for, you can have it as long as you have a powerful reconfigurable core in your circuit. Okay, so now we're jumping into examples. Into actual applications that we have demonstrated. The first one is for microwave photonic links, which is transmission of microwave signals through an optical fiber.
понятно, что мы с помощью разъясняем перестроение логического применения.
Okay. Okay. So there are different means of transmitting a signal, a microwave signal through an optical fiber network, but all of them need modulation, either amplitude modulation, phase modulation, or equivalently frequency modulation, right? But if you do amplitude modulation, you can use a single detector, okay? If you use a phase modulation, maybe you can use a coherent receiver that we saw yesterday with another laser, etc. And if you do frequency modulation, like this one, lower frequency, higher frequency, you can use a discriminator, okay? A discriminator is something that for people at the RF world is very well known. It's actually something that tells you when your frequency is on the lower range or on the upper range. Basically, it translates a frequency change into an amplitude change. Okay? A frequency discriminator, as I said, can be, for instance, like this, splitting your signal in two parts and then having two filters. One filter that lets you pass the upper part of the spectrum, and then the other filter that lets you pass the lower part of the spectrum, the red and the blue filter. Okay? So, and then with a balanced detection, you can rectify the wavelengths because you get this and this, this from the blue filter, this from the red filter, but then you invert the sign of half a period with a balanced detector, and you have rectified your waves. Okay? So we did this on a photonic integrated circuit, and you can clearly recognize that we use the ring-assisted Mach-Zehnder architecture. You can see here the Mach-Zehnder with a ring in the arm, one filter, and then a second filter here, second filter stage, one filter again here with a Mach-Zehnder with rings, and another one with Mach-Zehnder with rings. These rings are doing these filters, sorry, are doing the following. The first input filter is just to separate the upper sideband and the lower sideband. So it sends the upper sideband to this filter and the lower sideband to this filter. And then these two filters are the ramp filters, the ones that are actually rectifying your frequency. Okay? And then the output goes to a balanced photodetector. We did this in indium phosphide technology. These are indium phosphide waveguides. This is the indium phosphide chips. If I remember well, it was 6 by 6 millimeters square. You can see the size more or less. There are two chips here of this size. And this is the designed response for the input filter. It splits one band and the other band. And then for filter 1 and filter 2 and the combination. So basically, if you have a frequency modulation and your laser is here, when the frequency goes up, your laser goes there, then the amplitude goes up. When the frequency goes down, the laser goes here, so the amplitude goes up. And since you have this balanced detection, actually it is like having this slope the other way around, negative. Okay? This is the actual measurement, so this was the simulation. And this is the actual measurement of the device. Of course, you can see it is not exactly as we designed it. There are imperfections. As I have mentioned before, when you do these filters, even if you tune them very well, you get imperfections. One advice for you, if you are using photonic integrated circuits with thermal tuners, try to put them one a part of the other. Sometimes it's not easy because you need very high integration density. But then there is thermal crosstalk. Okay, so you try to tune this ring, but you're also tuning this one with this same tuner. Okay, so you need to compensate and to iterate until you find something similar to what you designed. Okay? So this is the filter response, and we did as well a typical two-tone probe response to characterize the nonlinear response of the RF system. If you are familiar with RF engineering, you've seen this, for instance, in amplifiers. And you use two tones at the input, okay? And then at the output, what you get is actually the two tones, but also the intermodulation tones, and also the harmonics there. So the intermodulations that fall near to your tones are the ones that you use to measure which is the relative amplitude and to state which is what is called the spurious-free dynamic range, okay? The range where you actually, here, the spurious-free dynamic range, the range in dB where you don't have any spurious tones, okay? Where your system is to be considered linear. This is the base noise, and this is the spurious free dynamic. I'll skip this one and this one, okay? Any question on the frequency discrimination? No? Okay, now let's go to another one, which is also interesting in RF, which is the instantaneous frequency measurement. I draw here this, or my student draw here this military application, but it also has civil applications, right? For instance, in LTE mobile systems or 5G mobile systems, where there are systems that the frequency is rapidly changing, and your receiver needs to find which frequency it is to tune to that frequency, right? And for instance, in this case, you need to identify which frequency it is, maybe to jam it from your plane to the missile. Okay. So this can be done as well with this type of filter. How? You have again the typical architecture of an RF photonic system, as I said, laser, modulator, the filter, but in this case, two detectors. Okay, two detectors. And your Mach-Zehnder modulator, you bias it in such a way that you suppress your optical carrier. That is, you bias it at a low point. Okay? You are familiar with Mach-Zehnder, some of you, and with biasing. That means that if this is your optical carrier and you modulate in double sideband, then you will get these two bands here and somehow a suppressed optical carrier. Okay? And when you do that and feed a filter which has complementary response, and this is important, complementary means if you go from this port to the upper port, you have this response. And if you go from the same port to the other port, you have actually the complement response, like in a Mach-Zehnder. Okay? This is a Mach-Zehnder, but a little bit more advanced. Then you can do the following. Let me skip this and go to the sort of animation. You can do the following. Okay? Imagine that you have an unknown frequency here and that you modulate in such a way with at the pi point in such a way that you reduce the carrier. And this is the unknown frequency. Okay? What happens if this frequency changes? Have a look at this and this. Okay? Here what you are taking is the DC ratio between the detection of this and this. Okay? So what happens is that the frequency changes, the amplitude value, the subbands C changes. And the ratio between them changes. Okay? So basically, what you get is a function which is called amplitude comparison function, which depends on the RF frequency. And you did it by photonic means. Okay? That means that if you calibrate your system and have this function stored maybe in your processor, and you get this amplitude, then if you get this amplitude, then you immediately can tell which frequency, RF frequency you are receiving. Okay? Is that clear? Okay, we can see it once more. As I said, low bias, keep only the power on the sidebands. Ideally, you would suppress all this, but in practice you cannot. And then, when the frequency changes, the response these sidebands see from the filter is different. There they see high amplitude, low here, then lower, higher, lower, higher, lower, higher. And then, since you are doing the ratio, you have a range where you can univocally determine the frequency. Okay? We did this with the same chip, actually, with the input filter. And then the input filter has two complementary responses. These are the ideal ones and these are the measured ones. And then we compute the ideal amplitude comparison function and we measure one. Okay? So actually we know if we get like 0 dB in the ratio between this and this when we measure, actually that corresponds to 10 gigahertz frequency. Okay? The differences between the ideal and the measured are due to something that I have already mentioned. For instance, it is impossible to totally extinguish the optical carrier. Okay? That means that these peaks here are not peaks but are smooth. When you simulate the same system but with the finite extinction ratio, you actually approximate very well what you have in this one. Okay. I'll skip the noise. questions on this second application? One question.
Там FM это частота модуляции, верно? FM это частота модуляции Махазандера.
Yes.
Phi with index m, it's frequency, modulation frequency.
Yes, there is a modulation frequency.
Okay, this application help us not use photodiode, for example.
No, it uses photodiodes, but these are DC photodiodes. These are not high-speed photodiodes. There are other proposed RF photonic techniques to make this instantaneous frequency measurement, but they use high-speed electronics. Our implementation does only use DC electronics.
So what is this deep of modulation? Deep modulation.
The depth of modulation here needs to be such that it's linear.
How many percent?
How many?
Percentage.
Oh, I don't remember which percent was, but I don't remember the VPI, but only part of the VPI, maybe I don't know 20% of the VPI, just to stay in the linear part of your Mach Cinder, because if not, you will get harmonics here.
Usually use 70%.
70%.
Effective modulation.
Okay. Any other question?
Everything, all that was presented here is for application for transferring and receiving information.
Well, no. The previous one was for transferring information, and this one is for detecting a frequency, just a frequency detector. Okay. And the next one is a microwave filter, but done with photonic techniques. Okay, which is reconfigurable, and it is. I'll skip this one. Basically, it is this filter. Okay. This filter and this chip is 6 by 4 millimeters square, and it has two lasers, DVR laser. This is wrong. 2 DVR lasers, one Mach Cinder modulator here, the optical core, which is a Ramsey filter, actually implements a Chebyshev 2 tunable filter, the photodetector here, and then auxiliary ports. Okay, auxiliary ports. So this works in coherent mode. Yesterday we discussed how to do microwave photonic filters, coherent regime and incoherent regime. Okay, this works in coherent regime. Actually, you have a laser, you modulate in a single sideband fashion in such a way that you only have a single sideband. This is your optical filter, and depending where you put your optical carrier and the distance of the subcarrier in the RF domain, when you bit them together, you will see one or other type of filter. Okay, if it is closer, you will see a wider filter. If it is far away, you will see a narrower filter. Okay, so it's a matter of translating this filter from the photonic to the electronic domain, and to tune it not by tuning the filter, but by tuning your laser. Okay, so you change the laser position, the equivalent filter in the RF domain changes. Okay, so these are still simulations. What we did is in this case in BPI photonics software, we put the same design parameters as we designed, and we got the filter response that we designed. These are single sideband modulation signals done with the BPI as well. This with the single sideband here, and the different colors indicate different tuning positions inside the filter. So the filter, as I said, is fixed, and we tune the input signal in such a way that we see either this filter or this a little bit more wider filter. Okay? This is with the two detectors, so we have also complementary responses here, this one, and the equivalent complementary here. Okay? And this is the actual chip, and well, all this is the same architecture. And let me go to the interesting part. There are a lot of graphs here. For instance, this one. Okay, let me skip to this one. Basically, what we do is we modulate and we tune the laser. The filter is fixed. Okay, so we tune a little bit the laser, only a little bit, Imagine that the free spectral range of the filter is periodic, so actually the periodicity is around 20 gigahertz. So we actually need to tune the laser only at a few picometers to scan those 20 gigahertz, a few picometers. And when you do that, this is the filter that changes, okay? It changes not in a nice manner because there are imperfections there that I will describe later. Ideally, one would like that if this is the starting point, the red curve, that the red curve without changing the shape moves left and right. This didn't happen in the experiment. This was ideally should happen that, but in the experiment we didn't find that, and we know why, and I'll tell you later. Okay, but actually we got here 3 configurations in which you can see that you can reconfigure the filter and you can tune it a little bit, and you can see the different passing bands are wider or narrower. Okay, there are things to consider when designing these chips that it's important from a practical aspect. One thing is polarization rotation. Okay, the lasers will emit light in TE mode. Okay, TE mode usually it's by convention is associated with the plane of the chip. So this is the chip, the laser is sitting on the chip, the light is emitted with polarization parallel to the chip plane. Okay, but then this laser, if I can scroll back here better, this laser goes into a bend, a bend, a bend. Bends are very special waveguides, because if you don't do the sidewalls straight and do the sidewalls like this, the polarization axes are tilted with respect to the straight waveguides. That means that even when you go with your straight waveguides with one polarization, then instead of hitting this polarization and nothing of this, it hits like this. So actually you are exciting this polarization and this polarization. The filter is designed to work for TE polarization. So that means you have polarization bitting, and when you tune the laser, you change the polarization bitting, and you are changing the filter shape. Okay? So that is one thing that you need to take into account. Polarization, if you have waveguides that support the 2 polarizations and you have bends, please make sure that either your bends would only support 1 polarization, or that the radius is such that with the sidewall angles, which you cannot avoid because those are done in fabrication, you don't have polarization, conversion and rotation and loss. Okay? Other important issue is RF. Okay? RF. We have here the modulator patch, and we have here the detector patch. We found that we had a lot of RF crosstalk. We still have not determined whether it is on the photonic chip or on the RF subcarrier. But this we did it adhering to a packaging template, and the packaging template states here RF and here DC. Perhaps if we did it custom, we have put this maybe on the other side, or here and this far apart. Okay? So that's another recommendation. Templates are nice for a proof of concept, but then are surprises. Okay? In our case, RF crosstalk. Okay? These are the linear measurements, and we also did the nonlinear measurements as in the other RF experiments. Okay, this we saw yesterday. You can skip to the conclusions already. Today we are going a little bit ahead of time, I think. Yes, that's fine. Okay, so in this second session, yesterday we saw one session, this is the final part of the second session. We've seen how convenient it is to process RF signals in the photonic domain. But up to now, this has been done with discrete components and systems the size of this table, even larger, which is something not practical, something that you cannot carry with yourself, or that you cannot install in 1,000 antennas on the field. That is why there is a strong push to make these circuits, these photonic integrated circuits, that allow for processing of RF signals in the photonic domain, in such a way that you can put them elsewhere. There is additional reading. I left some papers in the folder. Maybe if someone is interested in reading more on the topics. These are 3 good papers. Maybe this is more generalistic. This is more on aspects, and this one is related exactly to the filter I have presented as the 3rd application. Okay, and that is it.
Есть какие-то вопросы? I have one question. We have a lot of Alexander there, that tuning filter, and you need to during the fabrication. Also, it's not predicted in what state Alexander filter and Alexander interferometer will be.
Yes.
What's the procedure? How to test it correctly from left to right? How do you?
No. Okay. That question I can answer with. I mean, this filter is totally equivalent to this one. Okay, to the other one. And let me skip fast. This one was nearly there. So this is the idea, and this is what we measure with little tuning. Okay, with little tuning. So the fabrication and the design went quite well in the case of this filter. Okay, this filter we had access from the outside of the chip, so we could measure the transfer function. For the other one, we didn't have access, so we actually don't know how well it was, because we could not measure it externally. We had the polarization rotation issue. My feeling is that it was as good as this one, but with the polarization rotation, we had issues. In this case, since we are using polarizers at the input, everything is going well. Okay? So you can trust design and fabrication of these things from our experience.
But in case we need to, for example, to tune first to 1 MZM, then second MZM.
Yes, yes, that is the case. I did not closely related to the experiments of the mesh one. Just skipping of the mesh one, but the mesh one, that is true. It's a mess actually. The mesh one, it is true how to find in which state each Mach cylinder is. And they develop a procedure to iteratively, one by one, I set this one to this, okay, then next one, if I set it to this, I should get this or that. So actually to know which is the state of each Mach cylinder, and once you know the state and the variation of each one, then you try to do your filtering. Okay, but the first step is to learn how is your circuit after fabrication. Of course, not all are in bar, not all are in cross. It's a little bit arbitrary, because it's optical phase, and that depends on the roughness of the waveguides, and that is something unpredictable. Questions? Questions? No? Skip to the next?
Yep.
Okay. Okay, now we are changing topic quite a lot. The bio people is not here yet. Bio people is not here yet. No, don't call. What we can do is we do the mid-infrared and then the bio.
Just want to check 1 minute.
Okay, well, yeah. Okay.